All right, so let's look at the second lecture in our first module for circuits. This is going to define some basics. We're still in chapter 1 of the textbook. I'm talking about voltage, current, and power. So first we'll start with charge, which is the charge is the charge of an electron. So 1.6 times 10 to the negative 19 coulombs is a single electron charge, the fundamental quantity of charge. The flow of charge gives us current, and that's really what we work on in this class. Charge is drilling down a little deep into the physics of everything, but there's a good review here in chapter 1. Again, electron drift gets really into the physics of how things work, and we just like to assume current. The model here is when electrons move into a wire, they don't actually start here and you get the same electron out the end. This electron pushes on this electron, which pushes on this one, and so it's kind of like shoving a big tube full of jello, and you push on one end and jello squirts out the other end. So the actual travel time would be a really long time for how long this electron takes to move, but the actual information is traveled. This electron pops out the other side roughly at the speed of light. So that's a nice thing about electronics. The other thing that I'm sure you've been aware of is that historically a bad guess was made on which way charge actually flows. So we talk about current flowing from positive to negative, where physically, in the physics of the thing, the electrons move the opposite direction. So that's another reason we kind of stay away from looking at electrons, because everything gets backwards when you talk about electrons. So we're going to look at current as the main overall quantity for electron flow. So current, again here, opposite direction from the electrons. Current is I, so C was already taken, I guess, for capacitance, so we don't use C for current, we use I for current. I is the change in charge and time, so it's a derivative of your charge in an element, and it's amps are the units. So again, it's really our fundamental unit, so we don't really look into Q very much, but that is how current is defined. Again, current has a direction. You could draw arrows with your current, and this shows 5 amps flowing down, and you could also draw the arrow coming up, and then its value would be -5 up or 5 down. That's the same current. So if you have a minus sign, it means it's going in the opposite direction from the arrow, and you always have to have an arrow or else you haven't defined things well enough. All right, so here are some basic definitions. I is dq dt, so we can integrate both sides and find that the charge, the total charge, is the integral of current. So if we want to see how much charge has passed through an element, we can integrate the current over time. So if we're given a function of time like this, for t greater than 0, we have this many amps as a function of time. It looks like this. We can integrate it. So the integral of from negative infinity to 0, that part goes away. And then from 0 to t, we've got our function. So we put them in there. The other thing we can find is how much charge has gone from 1 second to 2 seconds. So this example is in the book. I won't spend a lot of time on it, but it's just basically applying this equation to find the charge. And if you want to find the change in charge from 1 second to 2 seconds, you can change the limits of integration, and you'll get your number of coulombs here. Most commonly, current would be constant in a DC system, so we'll see that a lot. Then the current comes outside of the integral. This I would just come outside, and you're just integrating dt, so things become much simpler. They're rectangle shapes, and so you can just multiply them together. But this is the general solution. Voltage is our other primary unit that we're using. Voltage and current are the big things in electricity. So voltage is dW dQ, so the energy in joules, the change in energy, over the change in charge, dq. So it's how much work it takes to push charge into a system, or how much work you get when you let the charge out of the system. So voltage, and again, we don't really deal with charge going forward here, so we talk about voltage as more of a primary thing. But it's a potential, and it's how much work it takes to push charge in or to let the charge out. You get work out of the system. So it's a potential. This is a water tank, a fancy one. And so a lot of the times there's a hydraulic analogy in electronics, because the equations for hydraulics and the equations for circuits are the same equations, and so that's why it's analogous. So potential energy, hydrostatic potential, is a lot like voltage. It's how much work it takes to put water up there, or how much work you get out of the system if you let the water out. It's important to realize voltage is a potential, so it's ready to go. It's how ready it is to go. It's not how much it's going. So current, which is our other big thing, means that electrons are actually flowing. Voltage means the electrons would like to flow or would not like to flow. But whether they are or not is a different question. So current, things are actively moving. Voltage is ready to go. So here we have a water tank again, and whether the water is moving in or out is not part of the potential of this water up here. So voltage is measured in the same kind of way that pressure is measured in a hydraulic system. And so the concept similar to gauge pressure, where we have a reference. So with a voltmeter, you always have a red and a black wire, and you put the black wire on your reference point, and then the red wire tells you the voltage relative to that point. So we generally choose one. It's part of our analysis to choose the ground node or the reference node. So here's a circuit diagram with a voltage source and a bunch of resistors, and we've labeled this node 4 to be the ground node. That means it's defined to be 0 volts. And all the other voltages at all the other nodes are relative to that. So if we were to probe with our voltmeter, we'd put the black wire here, and if we put the red wire there, we'd measure 12 volts. Put the red wire there and the black wire here, we'll find 6 volts. Red wire here, black wire here, we'll find 4 volts, because this is the analysis that's already been done for us. And this is an arbitrary choice. Often it is picked physically, so in things like cars and ships, they often put the ground on the metal chassis of your car or the hull of your steel ship, and then everything is referenced to that because it's easy to access. But it is arbitrary in our analysis. If you decide to change your reference node, so if we put the reference node up here now, you just subtract 6 from everything, because that will make this one 0 and move everything else relative. So we have 6 here, so we subtract 6 and now it's at 0. We had 12 here, we subtract 6 and now we're at 6. We had 4 here, and subtract 6, so now we're at -2, so negative voltages are perfectly fine. If I put the black wire here and the red wire here, I'm going to find -2 volts. That means this one is higher than that one. Sometimes we try to put the reference at the lowest voltage so that all our voltages are positive, but sometimes that's not practical either. So subtracting them to change your reference node. So most of the time in this class, the drawing is going to have the ground node already defined so that everyone does the same analysis and we can compare our answers. But if you have to move it around, this is the process. All right, so this is a picture of how to measure voltage and how to measure current using meters. And series and parallel comes up here, and it's important to not do these wrong. We measure voltage more often than anything else, and it's dead simple. You take the black wire, you put it on the minus side, take the red wire and put it on the plus side. This is now in parallel with this resistor, the voltmeter parallel with this resistor, and you can measure the voltage across the resistance. That's what you'd get with this setup. To measure current, we have to break the circuit and run it back through the meter. So here is an ammeter set up, and instead of the wire going straight through here, we break it and we run it into the meter and then back out of the meter to where it used to be. So you break the circuit and then you patch it through the meter so the ammeter, the current meter, is in series with the wire that you want to measure the current through. So it's important to do these right. If you put this meter, has basically zero resistance because we don't want it messing with anything. If you put that straight across this voltage source, thinking you're going to see how many amps are coming out of the voltage source, you'll blow the fuse. There's always a fuse protecting these. You'll get a ton of current flowing through. So it's very common in things like makerspaces where you can borrow voltmeters that the fuse is blown from people hooking up the current measurement wrong. So make sure it's in series. You'll get to practice this in the circuits lab. All right, so the next definitions here are power and energy. And hopefully you've seen these before in your physics class too. Energy, W for energy, is the integral of power with respect to time, which means power is the derivative of energy. The rate of expending or absorbing energy is power. So these are definitions that work for physical work like forces and power, or electrical work in energy. If we're doing it electrically, then amps times volts gives us power, a watt, and a watt times a second gives us energy. So joules is energy, amps, volts, seconds are the fundamental units, watts is power, joules per second, or amps times volts. So remember, amps and volts are generally what we're solving for in our analyses, and we calculate everything else after that. So we would take amps and volts and calculate power, and then power times time gives us energy. Energy is conserved, but it can be transformed. So sometimes energy goes into a system and comes out as heat. So electrical energy doesn't have to be conserved, but total energy, of course, is. There's a sign convention that comes up from time to time here in circuits. We have to decide what does positive power mean, and it's an arbitrary choice. But the convention is that positive power means it's delivered to the device. So if we have an element here with a positive voltage on this side compared to this side, and current flowing in the positive terminal, that's positive power. And this is the arrangement. For example, if this was a resistor, this is the way current would flow with the voltage on the resistor, looking like this. Resistors absorb power and get hot, and so that's positive power. Negative power then means it's supplied, so the current flows out of the plus terminal of a battery like this, a voltage source, and so that's the opposite sign convention here. So that's a negative power being supplied. So it's not necessarily intuitive, but they had to pick one. So supplying power is negative, absorbing power is positive. That way power balances around the system. So the power from the battery, negative 36 watts. The power absorbed by device 1 here, the plus and the minus, and the current flowing from plus to minus, positive. All right, so the last little bit for today is Ohm's Law, which I'm sure you've seen before. V equals IR. Voltage equals current times resistance. So resistance is the value of the resistor, how hard it is to push electrons through, and that's measured in ohms. I is current in amps, V is voltage in volts. So you've seen that before. It's important to realize there's a sign convention with this because current has a direction and voltage has a polarity. If you switch the plus and minus, you flip the sign on voltage. If you flip the direction of the current, you flip the sign on the current. So Ohm's law is defined with positive V equals positive I times R if the current is flowing from plus to minus on that element. So the same as that power. This is really important because we'll be using this, and if you get the signs wrong, it's a system of equations and everything falls apart. So pay attention to the sign convention on Ohm's law, otherwise it should be really easy. All right, so that's the end of the second lecture in Module 1 for our class. And the last module will talk about power, current, and voltage, and the sources of power. See you in the next video.